For all those of you who are joining us so far, we're going to give another minute or two for people to kind of keep trickling in. I'm going to take the time to type some instructions into the chat window in Zoom on how the webinar is going to run today. Okay, great. We've given people enough time. I'm sure people will continue to trickle in, but we can go ahead and get started. So welcome to another one of our IR Science Interest Group online webinar series. I will be moderating the webinar today. My name is Meredith McGregor, and I'm an assistant professor at the University of Colorado Boulder. I'm also one of the co-chairs of the IR SIG Leadership Council, along with Mike Semkoff. A few brief instructions before I introduce our speaker and get started today. I've typed these into the chat window as well, so you can refer to them later, but I'll say them aloud now. Please submit all of your questions for our speaker through the Zoom chat window. If you don't already have that open, you can mouse to the bottom of the Zoom screen and click on chat. That will open up a chat window, and you can go ahead and type questions into that. You can submit your questions as they come up. You don't have to wait till the end of the talk. Then during the Q&A period that we have at the end of the talk, I will read questions to our speaker. If you would like to actually ask your question to the speaker directly, then you can use the participant window and the raise hand function. So if you also mouse to the bottom of the Zoom screen and click on participants, there should be a little button that says raise hand, and then I'll be able to unmute you and allow you to ask your question directly to our speaker. You can also submit additional feedback, comments, or questions for the IRSIG Leadership Council, again, through the chat window. We'll wait to answer any of those questions until the end of the hour. And if we don't get to them, we can always send you an email response afterwards if we run out of time. Or you can, don't hesitate to contact any of us on the Leadership Council directly. You can report technical difficulties in the chat window. That will help us address them if they come up. And lastly, this webinar is recorded and it will be available to view later on our webinar webpage, and the link again is provided in the chat window. So that's all the instructions for how this is going to work today. And with that, I will introduce our speaker. So today we're lucky to have Dr. Justin Spilker, who's currently a Hubble postdoctoral fellow at the University of Texas, Austin. Justin did his PhD at the University of Arizona, and then he's been at UT Austin first as a Harlan J. Smith postdoctoral fellow and now as a NASA Hubble fellow. So with that, I will turn it over to you, Justin. Take it away.
All right, thanks so much. See if I can get my slides shared here. Did that work? No, you have the presenter view. Is that true?
I can see it. I think you're good.
Oh, well, now I've just made it go away. So I will try again and just do the exact same things I did before. It's amazing how we can test this and then I immediately mess it up when we go to actually do it for real.
There you go.
Okay. Are we good?
Yep.
Okay, great. Yeah, so thank you everybody for being on this call today. I'm really glad to be here to speak. Thanks to Meredith for inviting me to give this talk today. So I wanted to spend the hour today talking a little bit about work that I'm doing, trying to understand this problem of galactic feedback. And if you're following the archive, you tend to see several papers every day on this topic. So I don't want to claim to be the only person doing a lot of work on this in this area. But I think one of the reasons that it has become such a big deal is that it basically touches on a whole bunch of different aspects of galaxy evolution. So today I'm going to try and address a few of those things over the course of the next hour. So just by way of a little background, I wanted to start off with there we go. This image of the Hubble Deep Field, which is now about 25 years old. And as we look out on this, we see just a field of galaxies of all different distances and of many different types. But of course, as we remember from our Astro 101 classes, you can sort of broadly distinguish these, even by eye in this image, into a couple main types, right? So we have these sort of red, poofy, elliptical galaxies. The fact that they're red tells us that they haven't formed any new stars in the past billion years or more. And we also have these big, beautiful blue spiral galaxies like the Milky Way that we live in. And the fact that those are blue, of course, tells us that they are forming young stars, and we're seeing that blue light coming to us directly from those stars. And of course, we can do this a little more quantitatively. Here's just one example looking at the distribution of colors from the Sloan Digital Sky Survey. And again, we sort of see that bimodality in galaxy colors where we have a strong blue population and we have a strong red population and not all that many galaxies in between. And this isn't the only way that galaxies sort of split into bimodal population. They also split up into a bimodal population in terms of stellar mass, where we see that basically at the highest masses, we find almost all quiescent galaxies. And at the lowest masses, very, very few galaxies are quiescent. They're almost all star forming. And there's sort of a smooth transition as a function of mass as we transition from star forming galaxies into quiescent ones. And they're also sort of bimodal in actual physical size. This is work from 3D-HST and the Candles team, led by Arjen van der Wel, where you basically see that as time goes on from redshift 2-ish down to today, the population of galaxies that are quiescent tend to be much smaller at a given mass than the star-forming galaxies. And that difference sort of evolves over time. So basically, as at redshift 0, they're relatively similar in size, but as you go out to redshift 2, that difference in sizes becomes more and more extreme. And just to give you an idea of what that looks like in terms of images, here's just a few examples of typical star-forming galaxies at redshift 2 on that top row. And you can see that they're basically starting to look something like what we think most star-forming galaxies today do. You can see evidence of spiral arms. You can see that those blue colors have remained. But on the other hand, the quiescent galaxies at that time were incredibly small, sizes of about 1 kiloparsec. And I promise this isn't just the same galaxy that I've copy-pasted 3 times. They just really all look very similar like that. And so that tells us that the structural differences between star-forming and quiescent galaxies were really exaggerated at high redshift. And so my research is sort of focused on trying to answer this question of how does this end up happening, actually? How do you halt and prevent star formation from a star-forming galaxy to turn it into one that hasn't formed stars? And how do you keep it from forming stars for billions of years? How do you sort of connect that, bimodality and structure with the similar bimodality in star formation? And what are the physical processes that allow us to regulate star formation through the history of the universe? And so that brings us to feedback, which is at some level a really catch-all solution. This is basically an umbrella term for a whole bunch of different physical mechanisms. But it basically touches on a whole bunch of different issues in galaxy formation. One of those is that feedback allows us to connect dark matter halos to the galaxies that they host. So if you basically make a plot of the abundance of dark matter halos as a function of mass, you get some, oh, isn't that lovely? Meredith, you're gonna wanna ban somebody, I think. You get a dark matter mass function that looks something like this. And if you were to do a similar sort of thing with the stellar mass of those galaxies that live inside those dark matter halos, thank you, you find that there's a sharp difference between the dark matter halos and the stellar masses of the galaxies that live inside them. And in particular, at the high mass end and at the low mass end, we find that there's a really sharp drop off in terms of galaxy stellar masses compared to the dark matter halos. We also know that feedback is one way that you can connect the supermassive black holes that live at the center of galaxies to the galaxies that they live in. This is the famous M sigma relation, where we basically find a strong correlation between the stellar velocity dispersion, or between the mass of stars in the bulge and the black hole mass at the center of those galaxies. And so feedback is probably involved in setting the normalization and scatter of that relation. We also know that most of the metals, most of the heavy elements that stars produce end up not living inside the galaxies that they live in. They end up out in the sort of tenuous circumgalactic medium, out to hundreds of kiloparsecs outside of galaxies. And I'll talk a lot more about that in a little bit. And somehow we have to move those metals that stars have produced out into much larger distances outside of galaxies. We know that feedback has to set the efficiency of star formation. So basically, if you have some amount of molecular gas, how much of that molecular gas is actually going to turn into real stars? Feedback is involved in setting that actual efficiency of how well that works. And of course, we need some way to actually quench star formation and keep it that way over many billions of years. And so, with a physical process or physical processes that touch on so many different areas, it's hard to come up with sort of one smoking gun observational test that you can do that will answer all of these questions, that will tell us, what is the key, scaling relation, or what is the key physical insight that is allowing all of these, sort of complementary correlations to come into play. But as an observer, I want to spend most of today talking about one of the most extreme and most visible, one of, in my opinion, the coolest ways that feedback manifests, and that's through galactic winds. And so basically, we know now that almost all galaxies, at least in the nearby universe, show evidence of these galactic winds. Doesn't matter if they're star-forming galaxies or AGN, we tend to find outflows. And so, for example, here on the left is an image of M82. This is the prototypical sort of starburst-driven wind, where there's a starburst happening in the nuclear regions of this galaxy. And that's resulting in a lot of different material being blown out along the minor axis of this galaxy. You see sort of a similar thing in this AGN-dominated galaxy. This is Sen A. But in this case, you're seeing the jets of the AGN come out as radio lobes. And with VLBI, you can track that down to the black hole at the center of that galaxy. And so obviously, with any image that looks as complicated as the wind does in here, you can imagine that these winds are very sort of complex physical systems, and that's true. And basically our issue is that the gas in these outflows spends many orders of magnitude in both temperature and density. This is just a cartoon that Adam Leroy put together to demonstrate the galactic outflow in M82. The point is not necessarily for you to read all of this text. The point is that there's a lot of text, and that's how you know this is a very complicated situation. And a similar sort of story emerges from simulations, where we find that if you attempt to accelerate a wind from a galaxy, you very naturally sort of emerge with a temperature and density structure that spans all of these orders of magnitude in those parameters, in that parameter space. And so that tells us that we can basically trace these outflows across all wavelengths, from the X-ray to the radio, and that if you only observe a wind with one particular tracer, you're probably only seeing a small fraction of what's really going on in the physical system. And so today I basically want to spend a little bit of time talking about two different aspects of things that I'm working on related to galactic winds. And given the crowd, I'm mostly going to focus on sort of new ways that we can use far-IR and submillimeter observations to probe feedback and outflows and winds across cosmic time. So I'm basically going to start off with one sort of project that's very much still in the works, very preliminary, that I think we can use possibly into the future to trace the rise of metals, to trace the metal enrichment of the universe, and the distribution of metals out onto large scales. And then I'll spend probably more of the time talking about some work that I've been doing for the last couple of years, trying to assemble the first statistical sample of molecular outflows in the very high redshift universe. And so one of the interesting things I think about the metallicity of a galaxy, it's very easy to sort of just say, oh, we know the metal contents of this galaxy. We know that, at least in our sun, only about 2% of the mass is contained in heavy elements. But the metallicity of a galaxy is sort of a surprising and I think really interesting consequence of this huge range of physical processes. So we have, metal pore accretion of gas from the cosmic web. We have metal enriched outflows of gas that are sort of spewing gas that was inside of galaxies out into the circumgalactic medium or beyond. And of course, we also have the production of heavy elements within stars themselves that then maybe explode as supernova or eject stellar winds that are able to enrich the gas that's inside galaxies. And so given all of these, really complicated physical processes that span scales from, tens of AU out to many hundreds of kiloparsecs, it's sort of amazing that, we get, in the end, this really tight correlation between the mass of a galaxy and its metal contents. So all of that sort of complex physics, at least on average, comes down to a relationship that looks something like this, where we find that at a given stellar mass, as you go further and further into the history of the universe, galaxies become more and more metal poor. And that sort of correlation holds across stellar masses and across redshifts, which I think is kind of cool. But there's a few problems with this picture, I think. And so one of those is that we know that galaxies that are really dusty, where the star formation is happening obscured by dust, dominate over all star formation in the history of the universe, at least out to about redshift of 6. So this is shown in a plot here by Jorge Zavala in an upcoming paper, where the orange basically shows the contribution of dust-obscured star formation, and blue, the unobscured star formation that you would normally trace in the ultraviolet with a telescope like Hubble, for example, as a contribution to the total star formation rate density of the universe. And you see that at least out to about redshift of 4 and maybe as high as 6 or so, the obscured star formation dominates over the unobscured. And so this could prove to be kind of problematic if our typical metallicity indicators that we use are coming from rest UV lines or from optical lines, which are very common and very easy to observe with ground-based telescopes today. And the second, as I've sort of alluded to already, is that we know now that 90% of all metals that stars produce in the history of the universe don't end up staying in the galaxies where they were produced. If you sort of add up all the metals that we can measure in stars, that's this red line, all the metals that are in gas, and all the metals that are in dust, you find that they don't come anywhere close to the total yields that we expect for the production of stellar populations. And so something has happened to all of those metals that has made them not remain within the galaxies where they were produced. Excuse me. And so I think part of these, we can come down to these observational effects. The typical way that one would go about measuring a metallicity, apologies if this is too simplistic, this comes out in your ISM class in grad school probably, but the gist of it is that you want to measure multiple lines of atoms like carbon or nitrogen or oxygen. And the relative line ratios that you measure tell you something about the temperature of the gas that's emitting those lines, or the density of the gas that's emitting those lines, or the ionization state. And the gist of it is that you basically want to constrain as many of those properties as possible so that the only thing left is the actual elemental abundances. So here's just a couple example line ratios that are fairly commonly used that constrain the temperature and the density of the ISM gas. And once you have that, you can sort of estimate the metallicity or the abundances. And so there's a bunch of different of these calibrations that you can imagine. And so the question is, well, how well do they agree? And the answer, shamefully, is not very well at all, actually. So this is a compilation from Lisa Cooley, where basically each of these different lines is a different calibration that someone has proposed for a way to measure the metallicity from these optical and UV lines. And you can see that basically at a given stellar mass, all of these different metallicity indicators give you about a factor of 3 variation. Even though they should all agree, even though we think that they're all measuring something that we're going to call metallicity, quote unquote. And so a lot of these variations, I think, come down to the problems that we have in our assumptions. So you have to, for example, assume the temperature of the electrons in an H2 region, or you're systematically affected by dust along the line of sight, which preferentially obscures or causes extinction for some of these lines, but not as much for others. And so I think that leads to a lot of the scatter that we sort of see in these plots. And so since this is a far IR focused group, I think it's no surprise that I think we can do much better using the far infrared. There are multiple advantages to doing this. For one, the temperature is mostly irrelevant because the temperature of an H2 region is 10,000 Kelvin or more, which is much more than the energy level of the lines that we're looking at. We don't really have to worry about dust as much because we're at very long wavelengths, and we can actually constrain other parameters like the density and the temperature and so on. And so here, this plot on the upper right is just one example of a calibration for a far IR-based metallicity indicator that has been proposed. There's several others. This one, as it turns out, uses the two far IR lines of O3 and the far IR line of N3 at 57 microns. And you can see that for a wide range of physical conditions in terms of the density or the ionization field, we can get a pretty robust metallicity out of this line ratio, which I think is kind of fun. And so I've been working over the last year or so on a project to use SOFIA actually to try to calibrate a metallicity indicator like this. And so we're trying to basically assemble some low metallicity dwarf galaxies in the nearby universe, preferentially focusing on ones that already have Herschel spectroscopy just to save on time, and to supplement that Herschel data with new observations from SOFIA, looking at the 52 micron line of O3 or that N3 line of 57 microns. And the idea is that basically with a combination of new data and archival data, we can try and figure out if this actual metallicity indicator works. And so I'm happy to say that at least preliminarily, we're getting some detections. Here's an example from an undergrad who worked with me through the Taurus program at Texas. This is an undergrad summer research program that's designed and premised around the idea of needing to get underrepresented minority students into astronomy. And so we basically take students from universities around the country that don't necessarily have a lot of astronomy research opportunities available, and try to give them what's basically their first research experience. So Gabby worked with me a couple summers ago, and she was able to pull out, for example, this line of the O3 52 micron detection from PhilLS. And so throwing all those together along with some additional data from my programs, it looks like indeed, yes, we are able to recover the metallicities of these galaxies over roughly 1 dex in metallicity. So this ends up stopping working by the time you get down to about 0.2 solar metallicity. These lines end up not working very well anymore. As long as you're above about 0.2 solar, it looks like, yes, in fact, empirically and motivated by models, this metallicity indicator works. And so what's kind of fun is that now that we have this metallicity indicator, we can actually use it to trace the distribution of metals across cosmic time. As I already mentioned, 90% of all the metals that are produced by stars don't remain in the galaxies where they were created. But our issue is that the starbursts that drive those winds that probably transport the metals are really highly obscured, right? So a galaxy like ARP-220 or like M82, these are really highly obscured galaxies in the actual starburst regions. So we need something like this far IR metallicity indicator in order to really probe down into the regions where the outflows are actually being launched. And so this is the part of this analysis that's really still very preliminary. I've been working on a program using resolved PhilLS data on M82, that prototypical galactic wind. And the idea is that we're basically going to try to map the metallicity out into the outflow of M82 and compare that with a disk. So I don't have a whole heck of a lot to show about this yet. I just wanted to flash that this really does appear to be working. In the galactic disk of M82, we really easily, strongly detect N3, the 57 micron line. That's good because if we hadn't detected it, I would have been in big trouble. But the cool thing is that we'll be able to do this on spatially resolved scales in M82, and a future far IR space mission like Spilker or Origins can actually do this across cosmic time, basically by doing it in velocity space instead of in the spatial dimension. And so I think we're really trying to set the groundwork for a lot of observations that we can do in the future with these future missions. And the second half of this talk, I really want to focus a little bit more on the high redshift universe. And we're basically going to try to understand if we can assemble a statistical sample of molecular outflows in the early universe. And to do this, I'm going to basically focus on really highly obscured galaxies because they're incredibly bright. And so if you don't know what you're looking for, you start with the brightest objects out there and you work your way into fainter samples as time goes on. These dusty galaxies are kind of interesting, I think, because from a lot of circumstantial evidence, we think that these dusty galaxies are going to be the progenitors of the very earliest quiescent galaxies. So we now know that we have identified through near-IR surveys from the ground that quiescent galaxies exist already as soon as redshift 4. That's only 2 billion years after the Big Bang. And so if you put together that 2 billion years with the stellar masses that we observe, you find that you require essentially extremely high star formation rates in order to produce those massive galaxies so early in the history of the universe. And from that and from a lot of other circumstantial evidence, we basically think that these really highly obscure galaxies must be the progenitors of the earliest quiescent galaxies. And so as many of you I'm sure know, the really big advances that we got out of Herschel, Spire, and PAX have led us to now have samples of many thousands of dusty galaxies. Most of them are at redshift 1 to 2 or so, but with a tail that extends out to the very high redshift universe. And so we're now in the regime where we have incredibly large samples of these dusty galaxies, but unfortunately the Herschel data didn't really give us any redshift information. Of course, that really broad dust SED peak that we're all very familiar with doesn't really give you a whole heck of a lot of leverage in terms of constraining a photometric redshift. And so the sample that I've been working with, as probably many of you on this call know, I've been working on this for many years now, is from the South Pole Telescope. It did wide-scale mapping of primarily looking for CMB anisotropies at 1.4, 2, and 3 millimeters. But of course, fortunately for me, there are galaxies between us and the CMB. And SPT in the survey is able to detect those galaxies and assemble them into a catalog. And so the sample that I'm going to primarily be working with here are these very bright sources. And the convenient thing about those bright sources is that if you pick out only the brightest sources, you're overwhelmingly dominated by sources that are gravitationally lensed. So if you essentially have some model for how many galaxies of a given brightness you expect there to be, you find that if you pick out only the brightest ones, you can only produce those if you are looking at a lensed population. There really shouldn't be any galaxies that are that bright intrinsically in the universe. And so here are just a few really high resolution ALMA images of galaxies from the sample. The overwhelming majority of them are indeed gravitationally lensed, and that can give you really detailed views of what these galaxies look like in terms of their structure and their properties. I mentioned that redshifts have been a long bottleneck for dusty galaxy studies. And thank you to the many ALMA attacks over the years. We are now at the point where with the SPT sample, we have 98% spectroscopic completeness. So literally 98%, I think there's only 1 or 2 galaxies left that do not have a spectroscopic redshift. We have measured these using ALMA 3 millimeter data. And the redshifts range all the way from redshift 2 out to about redshift 7, with the median at about redshift 4. And so having put together this large survey of galaxies where we have spectroscopic redshifts on the one hand, and a really detailed view from lensing on the other hand, allows us to open up a lot of doors that weren't previously available to us. And so one of those is that I think this is a really great sample for observing molecular winds in the very early universe. And the outflow tracer we're going to use for that is this hydroxyl molecule, OH. And there's a lot of reasons that it's a really great tracer of outflows. It's a simple molecule, it's easy to form, its transitions are really, really strong, and galaxies are very bright at these wavelengths. The transitions of OH are out here in the far IR where the dust emission is very strong. We're basically going to look for these signatures in absorption of outflows. And so just to show you, this is the kind of thing that we're hoping to find, these really strong blue shifted line wings. And that blue shifted line wing basically tells you that you're seeing gas that is in front of the galaxy and moving towards you. So it's unambiguously an outflow. And so I've been working on a survey to basically put together a sample of about 12 of these high redshift galaxies, redshift 4 and above, trying to spatially resolve the molecular outflows in this sample. We can spatially resolve these because it's actually so easy with ALMA to detect outflows this way that if I just wanted to detect them, it would take about 2 minutes on source. And it seems pointless to spend 20 minutes of calibration in order to take 2 minutes of science data. And so many headaches have been caused by this decision, but I decided to try to also spatially resolve these outflows. And there's really good sort of theoretical motivation for wanting to do this. It's sort of illustrated here. The structure of a molecular outflow, kind of surprisingly to me, is actually a really useful constraint for simulations of outflows and winds and feedback. And the reason for that is basically that if you try to push on a cold cloud with a hot wind that you might expect is coming from supernovae or from an AGN accretion disk, you very quickly find that most of the cold molecular gas is shredded. You try to push on these cold clouds, and you just can't because the hot wind shreds them apart through hydrodynamical instabilities. And so basically what ends up happening in that case is that whatever cold gas you find in your wind is basically the coldest and densest regions before it started getting pushed on. So only these really small clumps, these few dense blobs are able to survive being accelerated out into an outflow. One alternative is that, after you have this hot wind getting out of the galaxy, you're at large radii, now that gas can start to cool. And if you're lucky, if the gas is still dense enough, maybe that once hot gas can reform molecules. And that tends to produce a much more sort of even distribution of molecules, basically because once the gas hits some radius, some cooling radius, it can turn into molecules. And so you tend not to have those few sort of blobby structures, but this much more uniform covering fraction, where all the substructure is on these really, really tiny spatial scales that we will never be able to resolve with any telescope, unfortunately. And so one of the first results that came out of this survey is that molecular outflows are really ubiquitous in this sample. So every source here that's surrounded with a green box, I am confident enough to say it is unambiguously an outflow. And these 3 objects that are in gray, we do detect OH and absorption, but it's a little complicated and I'm not 100% convinced that what we're seeing is actually an outflow. And so just this alone, this fact alone that we can detect all of these outflows and absorption tells you that A, outflows have to occur in essentially every single source, and B, they have to cover a big enough fraction of the source that we can detect them in absorption nearly all the time. And so those are 2 sort of conclusions that you can come up with without doing any sort of spatial analysis, without doing any complicated modeling, et cetera. We already know that these winds have to be both really, really common, and they have to, have these wide opening angles that allow us to see them in absorption almost all the time. But of course, we do have that spatial information. And so here's one example of how this works. Through a painstaking amount of work, we go through the process of gravitationally lens modeling all the ALMA data. And because we have very high spectral resolution from ALMA, we can separate out the absorption that is only coming from systemic velocities, only due to absorption within the galaxy, and the highly blue shifted line wings that represent the outflows. And so in this particular case, we published in Science a couple of years ago, we found that the systemic absorption, that gas that's inside the galaxy, basically just peaks in the center where the continuum is brightest. And that sort of makes sense. That's where the continuum is brightest, so it's easiest to detect absorption. That's where the gas column densities are highest, so you get a really strong absorption signature. But the structure of the outflow looks a little bit more interesting, I think. So at least for this outflow in particular, we found that the wind was dominated by these 2 clumps, maybe 3 clumps of absorption. And so that tells us that basically the wind is not, it doesn't look like it's spherical. It doesn't look necessarily like it's really concentrated towards the center, or at least it's not only concentrated towards the center. And instead it has this kind of cool, clumpy looking structure. And what's fun is that that clumpy structure is also ubiquitous, actually. So here's a sort of rogues gallery of 8 of the outflows from this program. And just sort of by eye, you can see that by and large, these outflows are in fact clumpy. essentially all of these, you find that the absorption, which is in blue in these maps, is not uniform. It tends to be separated out into sort of clumps on scales of a few hundred parsecs. And it's not, you don't have to just take my word for it. You don't have to trust your eyes. They're actually also quantifiably clumpier than the dust continuum. To make that statement, I'm sort of borrowing a few metrics that are most commonly used in observations of star-forming clumps at low and high redshift. If you don't know what these axes are, it doesn't really matter all that much. The point is that in the upper right quadrant of each of these panels, that's where we know that the absorption component is clumpier than the continuum emission by multiple different metrics. And so indeed we find that, indeed we find that about 6 or 7 out of the 8 outflows in this sample are quantifiably more clumpy than the continuum emission is. And so that's actually a sort of direct prediction that can be made and can be compared to high resolution simulations. These are all metrics that are sort of straightforward to derive from simulated images of an outflow. And so one of the interesting things, I think, is that these absorption lines are really highly optically thick. So what that means is that if you're looking at your spectrum and you see that 10% of the continuum flux has been absorbed, that tells you that 10% of the galaxy has been covered up by this outflowing material. And so I can compare that 10% to basically the covering fraction that I get from my lensing reconstructions, and use that to infer something about the spatial structure of these outflows on scales much smaller than what I've actually observed. And so the fact that this line, is optically thick tells me that we basically need something like 2 or 3 times higher spatial resolution than what we actually have in order to resolve the clumpy structure of these outflows directly. So you end up needing something like 50 to 200 parsec spatial resolution, which sounds crazy. Like, it sounds insane to map a galaxy at redshift 5 on scales of 50 parsecs, but that's actually achievable with ALMA and lensing, and that's one thing that I'm very much interested in doing into the future. So I focused a lot so far on sort of the spatial properties, the structural properties of these outflows, but I want to spend a couple minutes now on the more physical properties of these outflows, since that's something that people ask me about a lot. One of those is the molecular outflow rate. So here what I'm showing is basically a compilation of molecular outflows observed in low redshift galaxies. All of these little squares are from CO observations, and these circles are from other observations of OH, like what I have. And on the top here, we have the outflow rate as a function of the star formation rate. And on the bottom is the wind mass loading factor, which is basically just the outflow rate divided by the star formation rate as a function of the star formation rate. So objects with a mass loading factor greater than 1 are basically ejecting gas faster than it's formed into stars, and below 1 means that the star formation is winning compared to the outflows. And so through a sort of complicated set of inferences and models, here are the outflow rates and mass loading factors that I come up with for this sample. We find that the outflow rates are very high. We're looking at outflow rates of hundreds of stellar masses per year, but they are a bit less than the star formation rates, right? So we're not seeing these outflow rates that are much, much higher than the star formation rate, even though we're looking at really highly luminous systems. And so one of the sort of next greatest hits, you might ask what's actually going to happen to all of this outflowing gas. And the answer is that very little of it is actually going to escape the galaxies. Most of it is going to stay sort of in the near, central 100 or 200 kiloparsecs before it eventually comes back down as a fountain. And so this plot on the right is basically just showing as a function of the velocity of the outflow compared to the escape velocity, how much of the outflow mass has been contained. And so basically out here in this right half of the plot, that's all gas that is going to at least temporarily escape the galaxies, not necessarily the dark matter halos, just the galaxies, and sort of live out in the circumgalactic medium. And on the left is sort of a summary of those statistics. And we essentially find that somewhere between 1 and 50%-ish with a wide degree of scatter of the gas in these molecular outflows is going to escape out into the CGM. And so what that means is, as far as the CGM is concerned, is not a whole heck of a lot, actually. So here I'm showing the total mass that escapes these galaxies from these outflows, just as a function of the IR luminosity. And through a lot of Hubble work and a lot of ground-based optical work, we now know that at least in galaxies that host quasars at about redshift 2 or 3, these are massive galaxies, we find CGM total masses of about 10 to the 10 to 10 to the 11 solar masses. And in comparison, the molecular outflow masses that are actually going to escape out in the CGM are 1 or 10% of those values. So basically very little of the total CGM mass is coming out from this single outflow event. So that means that either you have to invoke a bunch of different outflow phases, warmer phases like atomic or ionized gas, or you have to sort of sustain these outflows over a very long period of time in order to slowly build up the amount of gas that we see in the CGM of quasars at slightly lower redshifts. But what's interesting is that it's actually maybe 10% or more of the total metals that we see in the cool CGM. This is a really sort of hokey comparison. All I'm doing is assuming that the outflows are solar metallicity. I have not measured the outflow metallicity. I'm just sort of guessing that if they're driven by star formation or even if they're driven by AGN, that it's going to be metal enriched to at least about solar metallicity. And what you find is that because the CGM as a whole is subsolar metallicity, that these outflow events can actually constitute a sort of highly significant fraction of the total metal mass of these quasars, which is kind of fun, I think. And so in the future, I think it will be really fun to actually apply that spatially resolved or that far-IR metallicity indicator that I talked about in the first half of this talk to these actual same outflows in order to get a much more robust measurement of the way that metals are being distributed out into large spatial scales. So I have another call after this, so I'm actually going to wrap up here. I'm sure many of you also have other calls after this, since we spend so much of our lives on Zoom now. So just to sort of summarize, I think what we have now been seeing and what I have come to appreciate is that the far infrared has a lot of these really powerful diagnostics of outflows. I think it's possible for us now in nearby galaxies and for many, many galaxies into the future to actually measure the enrichment of galaxies, the metal enrichment, and measure and track where all of those metals are being transported. And I've also shown using the first sort of large sample of outflows from ALMA that clumpy molecular outflows are very, very common in star-forming galaxies. This is something that you might expect, I assume. And basically future missions will be able to observe outflows like this in every star-forming galaxy out to redshift 2, which I think is a lot of fun. So I'll stop there and take any questions. So thanks.
Great. Thanks so much for a really excellent talk, Justin. So this starts our Q&A period. And as a reminder, you can feel free to type questions for our speaker into the chat window, or you can, if you would like to ask a question of the speaker directly, you can raise your hand in the participant window and I'll call on you and unmute you. So far, we have some comments. Many people loved your talk, Justin, which was excellent. And Lee Armis has a comment that says, it's hard to understand how this applies to the population as a whole without a bit more clarity on the selection of the targets.
Yeah, I completely agree. And I sort of washed over that a little bit. The answer is that the selection of targets were whichever ones seemed like they would be possible to observe a molecular outflow in. So in practice, what that means is that we span IR luminosities from a couple 10 to the 12 up to about 10 to the 13 at whatever redshifts happen to correspond to windows in the atmosphere where I can observe OH. So it's by no means sort of a statistical sample or a cleanly unbiased sample or anything like that. But again, I would just sort of push back on that and say, given that there's been a grand total of like 2 molecular winds detected at redshift 4 and above, I'm not super concerned yet at this point about making a really clean selection of targets and more just trying to assemble some sort of sample that we can point to and say, this is a sign that these observations are not a waste of time. This is something that I think we really need to focus on in a more cleanly selected sample. So yeah, I totally agree.
And we have another question from Alex Pope, which says, how are you getting the AGN fractions for the SPT sources?
Yeah, so those are basically coming from SED modeling, where the AGN fraction is mostly constrained by rest frame mid-IR observations from PACS. So basically PACS at 100 and 160 microns probes about 20 microns in the rest frame. And so it's really a mid-IR based AGN indicator. So that one is not, 100% foolproof, but it's really not bad either. It's much better than, things like the optical or the UV for these really dusty sources. But is it possible that these things are so dusty that they're optically thick at, these wavelengths? Yes, that's possible. And I think in order to really get at that in a better way, you would need really hard X-ray observations. And that will take quite some time, I think.
Another question from Lee, which says, can you tie your clumpy structures to the competing models of ejecting clumps versus forming clumps in the winds?
Yeah, I haven't pushed a lot on that front yet, mostly because I think it's still the case that we're only really resolving these outflows over about 5 to 20 spatial, resolution elements. If I try to sort of model what my spatial resolution is in these lensed galaxies, all of these outflows only span like 5 to 20 resolution elements. And so I'm really kind of holding off on doing that comparison to theory until we get a better estimate of, a bit higher spatial resolution. But I can show you, this is sort of the state of the art as far as simulating molecular outflows go. This one on the right where the molecules reform from a hot wind, you can tell that it's not even a spherical cow, it's an eighth of a spherical cow. And so the sort of realism in terms of how that's being done is not quite at the level where I really want to make a big deal out of these sort of comparisons. And part of that, to be fair, is because this simulation is doing actual full chemical modeling. And so they are doing a network of chemical reactions and actually calculating the abundances. So I really don't mean to put down this work. But I think I'd like to wait and see a sort of more realistic cosmological starting initial condition before really commenting on that. So yeah, thanks.
Great. Free to keep typing questions into the chat window. In the meantime, I'll just make the brief announcement that we have these webinars essentially the first Tuesday of every month. So we'll have another one at the beginning of August, always the same time, which is 1 p.m. Eastern or 10 a.m. Pacific time. So please join us for these webinars again in upcoming months. And if you are interested in speaking at a future webinar, or you have an idea for someone that would be a great speaker, please contact any of us on the Leadership Council with your suggestion. We especially invite suggestions for early career scientists of diverse backgrounds. And if there aren't any other questions, then I think we can let Justin have a break before his next Zoom meeting continues. So I want to thank Justin for a really excellent talk again. And thank you to all of you for joining us. And we hope to see you again on future webinars. So thank you.
Thank you, everybody.